On June 13th, 2026, the ground in Yellowstone National Park tore open. A 60-foot crack appeared without warning in Biscuit Basin, a stretch of geothermal terrain just north of the famous Old Faithful geyser. It filled with boiling water, hissed, and then 10 days later, it exploded. This was not a predicted event. It was a warning shot. And it was aimed at a story the world thinks it already knows. The story of a supervolcano, a geologic monster sleeping beneath America's pristine wilderness, waiting to erupt with a force thousands of times more powerful than any nuclear weapon ever built. An eruption that would bury half the country in ash and trigger a volcanic winter across the planet. The internet is certain it is overdue. The timeline has been calculated. The end is scheduled. What have you heard is the single biggest threat from Yellowstone? Tell us in the comments. The real answer is not what you think. Let's begin. The entire narrative is built on a misunderstanding so profound it borders on fiction. And the scientists tasked with monitoring the ground around that crack in Biscuit Basin are watching something else entirely. Something more immediate, more unpredictable, and in many ways, more dangerous than the myth. This is the kind of critical detail you won't get from cable news specials. A huge number of people watch these briefings, but a tiny fraction are subscribed. If you value this level of detailed analysis and you want to stay ahead of the official story, there is a button for that. It's the single best way to ensure you don't miss the next update. Here is what they didn't tell you. The supervolcano is not about to erupt. It cannot. But the ground beneath Yellowstone is waking up anyway. And the events of June 2026 are just the beginning of a chapter that will rewrite the geology of North America, whether the lava flows or not. Yellowstone was never supposed to be a threat. It was a spectacle. America's first national park, a landscape of impossible beauty, geysers, and technicolor hot springs. But in the 1960s, a USGS geologist named Robert L. Christensen began a lonely, decades-long project of mapping the park's ancient volcanic rock. What he found changed our understanding of the planet forever. He uncovered the evidence of 3 cataclysmic, caldera-forming supereruptions. They were not normal eruptions. They were planetary-scale events. The first and largest happened 2.1 million years ago. It is known as the Huckleberry Ridge-Tuff eruption. It ejected more than 2,450 cubic kilometers of rock, ash, and incandescent gas. To put that number in perspective, it is 2,500 times larger than the 1980 eruption of Mount St. Helens. Ash from that single event has been found as far away as California, Louisiana, and Iowa. It created the Island Park caldera, a collapsed depression so vast it dwarfs modern cities, an event that would have plunged the planet into a deep, sunless winter. Then, 1.3 million years ago, it happened again. The Mesa Falls Tuff eruption, smaller but still devastating. It spewed 280 cubic kilometers of material and formed the Henry's Fork caldera in what is now Idaho. And finally, 631,000 years ago, came the eruption that defines Yellowstone today. The Lava Creek Tuff eruption, a monster that ejected over 1,000 cubic kilometers of pyroclastic flow, carving out the 45 by 85 kilometer depression we now call the Yellowstone caldera. This is the source of the fear. The source of the countdown clocks online. Simple math seems to suggest a pattern. An eruption every 600,000 to 800,000 years. With the last one 631,000 years ago, the conclusion seems obvious. We are in the window. The clock is ticking. It is not a clock. It never was. Volcanoes do not run on schedules. The average interval between those 3 events is a statistical ghost, a number with no predictive power. Michael Poland, the scientist in charge of the Yellowstone Volcano Observatory, or WIVO, spends his days patiently explaining this to a world hungry for disaster. Even if you were to take that flawed mathematical average seriously, the interval is closer to 730,000 years. We would still have another 100,000 years to wait. But that is not the real reason an eruption isn't coming. The real reason is physics. The magma beneath Yellowstone is not a giant, sloshing pool of liquid rock ready to blow. That is a Hollywood invention. The truth, confirmed by decades of seismic imaging, is far more complex. The system is a magma mush, a vast, sponge-like body of mostly solid, hot, crystalline rock, with liquid melt trapped in the cracks and pores between the crystals. For a supereruption to occur, that sponge needs to be saturated. Scientists estimate that the melt fraction, the percentage of actual liquid in the reservoir, needs to exceed 50%. A critical threshold where the magma becomes mobile enough, buoyant enough, to begin its catastrophic ascent to the surface. Right now, the melt fraction in Yellowstone's shallower magma chamber is between 5 and 15%. Solid, mostly solid. The deeper, larger chamber is even less active, sitting at just 2% liquid melt. The volcano is not ready. It is not loaded. By the laws of geophysics, a supereruption is currently impossible. It would take tens of thousands, perhaps hundreds of thousands of years of new heat and new magma injection from below to raise that melt percentage to a critical state. The earthquakes everyone fixates on are not a sign of impending doom. They are a sign of a functioning system. The park experiences between 1,500 and 2,500 minor quakes every year as the ground breathes, moves, and adjusts to heat and fluid moving miles below. In June 2026 alone, the month the crack opened in Biscuit Basin, the WEVO recorded 118 such tremors. It was a normal month. In 1959, the magnitude 7.3 Hebgen Lake earthquake, a massive tectonic event just outside the park boundary that killed 28 people, failed to trigger any volcanic response whatsoever. The system is resilient. It is not on a hair trigger. If you were a visitor to the park, would you be more worried about a distant earthquake, a predictable geyser, or a sudden explosive blast of steam from the ground right next to you? The answer for scientists is clear, but tell us what you think in the comments below. So, if the magma can't erupt, what tore that 60-foot fissure into the earth in June of 2026? What is the real danger that park officials are quietly closing off entire sections of Yellowstone to protect tourists from? The answer is water, not lava. The greatest, most common, and most immediate geologic hazard in Yellowstone is not a volcanic eruption. It is a hydrothermal explosion. Michael Pollan has repeated this in public briefings for years. A fact consistently buried by the more sensational narrative. The park sits on top of an immense heat source, and it is crisscrossed by a plumbing system of fractures and conduits filled with water. When groundwater seeps down and comes into contact with rock heated to hundreds of degrees Celsius, it remains a liquid only because of the immense pressure from the rock and water above it. It becomes superheated. If that pressure is suddenly released by a small earthquake, a shift in the ground, or a change in the water table, that liquid water flashes instantly to steam. It expands to more than 1,500 times its original volume. The result is a violent, spontaneous explosion of steam, water, and shattered rock. No warning, no precursor. A kilometer below your feet, a pocket of water just became a bomb. That is what happened on June 13, 2026. A pocket of hyperpressurized steam found a weak point and blasted its way to the surface. This was not the first. In fact, it was the second major event in Biscuit Basin in less than 2 years. On July 23, 2024, a much larger hydrothermal explosion occurred at Black Diamond Pool. In the same small basin, debris was hurled 600 feet into the air. The explosion was powerful enough to be heard miles away. Park rangers shut the area down immediately. The WEVO scrambled to deploy monitoring equipment. They discovered that the explosion was not a one-off event. It was the beginning of a cycle. The ground continued to heave and vent for weeks. The June 2026 event was simply the next chapter, a confirmation that the shallow subsurface in this small, 2-mile stretch of the park has become dangerously unstable. These are not signs of an impending volcanic eruption. They are a threat unto themselves, a localized, unpredictable, and potentially lethal hazard that exists right now, today, while the world watches for lava. The ground is literally boiling over. The story of the thumper truck is an incredible example of human ingenuity. If you found that fascinating, hitting the like button tells the algorithm this kind of deep science reporting matters. And if you know someone who loves these kinds of stories, share it. It helps more than you can imagine. And I know we have mentioned it once before. But the analytics tell us a huge number of you watching right now still aren't subscribed. We have a problem we need to solve together. Let's fix that. But understanding why the ground is becoming more volatile requires looking deeper. Much deeper. For decades, the magma chambers beneath Yellowstone were theoretical shapes, their outlines drawn with the geologic equivalent of charcoal sketches. Seismic waves from distant earthquakes would travel through the crust, and by measuring how they slowed down as they passed through hotter, melt-filled rock, scientists could get a fuzzy picture of the monster below. It was not precise enough, not for a system this complex. So in 2025, a team of seismologists from the University of Utah and Rice University, led by researchers like Jamie Farrell, the EVO's chief seismologist, tried something radical. They decided to create their own earthquakes. They brought a 53,000-pound truck into Yellowstone National Park, a gigantic vehicle called a vibroseis, or more casually, a thumper truck. This machine is an earthquake on demand. It lowers a massive hydraulic plate to the ground and then vibrates it, slamming it into the earth with controlled force, sending carefully calibrated seismic waves deep into the crust. It's an ultrasound for the planet. By positioning a dense network of seismometers all around the truck, the team could listen to the echoes. They could map the subsurface with unprecedented resolution. In April of 2025, they announced their findings in the journal Nature. They had pinpointed the exact ceiling of the shallow magma reservoir. It sits 3.8 kilometers beneath the surface, 12,500 feet down. Not a range, not an estimate, a hard number. This discovery was more than just a technical achievement. It was a fundamental shift in understanding the volcano's potential. As Jamie Farrell explained, knowing that exact depth is critical. At 8 kilometers, the pressures are immense. That pressure keeps volatile gases, like water and carbon dioxide, dissolved within the magma mush. If that magma were ever to rise and the pressure were to decrease, those trapped gases would bubble out violently. One thing that makes these eruptions so devastating, Farrell noted, is that if gases are trapped, they become very explosive as they decompress. The thumper truck experiment didn't just map the magma, it quantified the explosive potential locked inside it. They now know exactly where the fuse is. They now know the pressure needed to keep the bomb from going off. And with every hydrothermal explosion at the surface, the question becomes sharper. What is happening to the pressure in that system? The story gets stranger. The magma chamber is not even fueled the way we thought it was. For half a century, the textbook explanation for Yellowstone was simple. It's a hot spot, the surface expression of a deep plume of molten rock rising from the Earth's core mantle boundary, like a giant blowtorch aimed at the underside of the North American continent. As the tectonic plate drifts slowly southwest over this stationary plume, the plume punches a series of holes in it, leaving a trail of dead calderas across Idaho's Snake River Plain, culminating in the active system at Yellowstone today. It's a clean, elegant theory, and it may be completely wrong. In April of 2026, a groundbreaking study published in the journal Science proposed a radical new origin story. It argued that Yellowstone is not fed by a deep, static plume at all. Instead, it's fueled by a shallow, eastward-moving mantle wind. The theory begins with a ghost, the ghost of an ancient tectonic plate called the Farallon Plate. Millions of years ago, as the Pacific Plate slid against North America, the Farallon Oceanic Plate was forced underneath the continent, a process called subduction. For eons, it has been sinking deep into the Earth's mantle. But according to this new research, a massive slab of that ancient broken plate is still there, lodged in the upper mantle, and as it continues to sink, it's creating a current. It is dragging hot, pliable astenospheric rock from the west and channeling it eastward, directly underneath Wyoming. This isn't a deep plume from the core. It's a shallow river of hot mantle rock, flowing horizontally, driven by the death throes of a tectonic plate that vanished from the surface long ago. This mantle wind is the heat source. Yellowstone isn't sitting on a stationary blowtorch. It's being fed by a moving, dynamic current of superheated material much closer to the surface. This is a paradigm shift. It reframes everything. A deep plume is a relatively stable, long-lived feature. A mantle wind driven by a sinking slab is a more complex and potentially more transient phenomenon. It changes our understanding of how long Yellowstone has been active and how long it might remain so. It changes the plumbing, the heat flow, the very architecture of the threat. The discovery that the magma chamber's roof sits at a precise 3.8 kilometers was a leap in knowing what is there. The mantle wind theory is a revolution in understanding why it's there at all. The science is moving faster than ever before. Another geophysicist at the USGS, Nympha Bennington, led a 2025 study that deployed a completely different technology, magnetotellurics. This method uses the Earth's natural electromagnetic fields, generated by lightning strikes and solar storms, to map the subsurface. Molten rock conducts electricity far better than solid rock. By measuring these tiny electrical variations across the park, her team was able to create an independent map of the melt, confirming the shape and size of the magma mush from a completely different angle. GPS stations across the caldera measure the ground rising and falling by centimeters per year as the magma system inflates and deflates like a slowly breathing lung. Satellite radar, called INSAR, produces color-coded maps of this deformation from orbit, revealing subtle shifts invisible to the human eye. River gauges measure the heat output of the entire system by tracking the temperature of the water flowing out of the park. Every tool in the modern geological arsenal is pointed at this one patch of ground. The Yellowstone Volcano Observatory isn't one institution, it's a consortium. A team of rivals from 9 different government agencies and universities, including the USGS, the University of Utah Seismograph Stations, and the National Park Service, all sharing data in real time. They are watching a system that is becoming more understood and yet more mysterious with every new discovery. And sometimes, clues come not from satellites or thumper trucks, but from the trees themselves. The landscape of Yellowstone is a living map of its last eruption. Not the supereruption of 631,000 years ago, but a much more recent, much quieter event. Around 70,000 years ago, on what is now the Pitch Stone Plateau in the southwest corner of the park, magma oozed to the surface. It wasn't an explosion. It was a series of slow, non-explosive rhyolitic lava flows that paved the landscape in thick, obsidian-rich volcanic rock. Today, if you look at a satellite image of that area, you can see the exact boundaries of those 70,000-year-old flows. They are delineated with razor-sharp precision by a solid, unbroken carpet of lodgepole pines. The surrounding areas have different trees or are open meadows, but the ancient lava flows are dominated by the pines. The reason is the soil. The rhyolitic rock weathers into nutrient-poor, sandy, acidic soil that other species of trees cannot tolerate. The hardy lodgepole pine thrives on it. The trees are a scar, a biological marker that traces the path of ancient lava. They are a silent reminder that the volcano has more than one mode. It can be a cataclysmic monster. It can be a silent, slow-moving creator of new land. And it can be a violent kettle of boiling water, all at once. The question is, which mode it is entering now? Some of the park's most famous features are sending mixed signals. Steamboat Geyser, the world's tallest active geyser, is capable of hurling water more than 300 feet into the air. After reawakening in 2018, it entered a period of unprecedented activity, erupting dozens of times a year. But in 2025, that activity began to wane dramatically. It erupted only 3 times in the entire year. And during the monitoring windows of early 2026, it fell silent. Is the plumbing system beneath Norris Geyser Basin, where Steamboat resides, losing pressure? Or is the heat being redirected somewhere else? Is it connected to the growing instability just a few miles away in Biscuit Basin? The geologists at the WIVO are asking these same questions. The system is a closed loop. A change in one location must have an effect somewhere else. A silent Steamboat Geyser and an exploding Biscuit Basin are not 2 separate stories. They are 2 symptoms of the same inscrutable machine shifting its gears deep underground. All this new knowledge forces us to confront the true scale of what Yellowstone is. It is not just one volcano. It's the current, active endpoint of a 17-million-year-old volcanic track that stretches across the entire Snake River Plain. It is a continental scale feature, powered by forces that shape the face of the planet. We now stand at a moment of stunning clarity and profound uncertainty. We know the volcano cannot produce a supereruption today. The physics of the magma mush make that a certainty. We have debunked the myth of it being overdue. But that scientific comfort is cold. Because we also know that the shallow hydrothermal system is dangerously active and becoming more so. We know that the ceiling of the magma chamber is a mere 3.8 kilometers away, a depth that makes the potential for explosive decompression very real, should the system ever become mobile again. And most unsettlingly, we now have a powerful new theory that suggests the entire volcanic province is fueled not by a predictable, deep plume, but by a dynamic, shallow mantle wind, a process whose future is far harder to forecast. We have mapped the monster with a thumper truck. We have seen its electrical signature with magnetotellurics. We have watched it breathe from space. And every piece of new information only underscores the immensity of the energy contained beneath the park. The real story of Yellowstone is not about an eruption that is coming tomorrow. It is about the permanent, powerful, and restless nature of the Earth itself. It's about the fact that the forces that built continents are not history. They are active processes, happening right now, just 12,500 feet beneath one of our most beloved national parks. The crack that opened in June of 2026 was not the herald of a supereruption. It was a message from a system far more complex than the myths ever imagined. A system that can change the face of America in countless ways that have nothing to do with lava. The ground is alive. The pressure is building. And the water is starting to boil. The story is not over.